finances, because money matters. If it doesn't make dollars and cents, it's not going to make sense. So we're going to learn about exponential increase and decrease, and talk about interest rates and the consumer price index, and we'll calculate the cost of electricity, or the bus bar cost. How do we get that cost? And we'll talk about the learning curve, or Moore's law, how with increased practice the price of much of our commodities reduces in time. So what if the economy grows at 10% annually and you have $100 invested in a technology? You should gain $10 on your investment and have $110 the next year. And will you have $120 the year after that? No, that's not correct, because you need to take 10% of the $110. And so that's 121. So each year, the value you have is what it was the year before times 1 plus 10%. And in year 3, you'd have 133. And you just multiply by 1 plus 10% 3 times. This is an exponential relationship. And this is what we see when we look at economy as a function of time, population as a function of time, growing exponentially, but we can graph it on a semi-log graph and we'll get a straight line because of the way logarithms work. When you multiply something and take a log of it, it's the same as adding the two separate logarithms, and with an exponent you can bring it out in front. If we were to make a graph of the log of your money as a function of time, it would wind up being linear in time. So if we graph the log of your value versus time, where time, the number of years, is in the exponent here, we should get a straight line, and the slope of that line should be the log of 1 plus the interest rate. And we can see this. Here we have, this is a graph of that same 10% per year. This is what you would have if you added $10 every year. This is what you get if the investment grows by 10% per year. You see, after a period of time, what you gain on your interest is much more than the original value of your money. Now, if we graph this on a semi-log graph, instead of putting the value of the money on the y-axis, we put the log of the value of the money on the y-graph. We see that the exponential curve is now straight. We see over 24 years, we get an increase in 1, and so the slope of this graph is 0.04, which is the log of 1 plus 10%. We see exponential decay for a number of natural things. One is the decrease in radioactivity over a period of time of a radioactive substance. So you see a 30-year half-life, you see a 230-year half-life. And the other is the decrease in the value of your money if you just hold on to it and don't invest it. So you see, this is how fast your money will decrease in value if you have a 7% interest rate, and this is how it will decrease in value under a 12% interest rate. We can get historical examples from looking up the consumer price index. This is essentially the value of money as calculated over time, as judged by the cost of commodities. And so this was done in 1992 dollars. So in 1992, $1 is worth $1. But if you have that same dollar in 1993, it's only worth 97 cents. So hanging on to your money will result in it having less value. If you could take that dollar back in time to 1960, it would buy you what appears to be $4.75 worth of goods in 1992. Let's make a deal. You give me $100 today and I'll return it next year. There'll be a lot of people who'd like to take you up on that. I might be a liar. You might not get your money back. Inflation, money is worth less. There's the opportunity cost. You could make investment gains with that money in the year. Why should you give it to me? Or something could happen. In any case, $100 is worth more to you today than it's worth to you tomorrow. The future value is discounted. So we use the term, a discount rate is how much less money is worth every year. So if I take $100 from you today, I'm going to have to give you more than that in a year. And so when we say, like, maybe I borrow $100 for 3 years on a 10% discount rate. The $100 is a present value of money you're giving me, and the $133 is the future value. And so we can write this present value times 1 plus the interest rate is raised to the number of years. And this is a formula we use, or the present value is equal to the future value divided by this number. So for calculating mortgages or car payments, I get a large sum of money now, and I have to pay it off over a long period of time. So we have calculus to show us how to do this infinite series, and we don't need to learn about that, but we can know what the numbers are. And that is, if you're going to make a number of uniform payments to pay off the present value of a house you just bought, this formula relates the amount of money you have to pay each year on an initial mortgage of this much money. This is the interest rate or the discount rate, and this is the number of years. And we call that factor the capital recovery factor or fixed charge factor. Say capital recovery factor, because it's the factor by which you recover the capital that you borrowed. So let's say you spend $10,000 on a 1 kilowatt photovoltaic system and it should last 40 years. How much does this cost per year? This is a $10 per watt system. That's pretty expensive, but let's just go with it. So you're going to take out a 40-year mortgage because it's over this 40 years that you will generate electricity with your investment. And you get an interest rate of 6%, you find that you have to pay $664 each year. Times 40 years, this is $26,000, which is way more than the present value. So why would you ever do this? Well, it's because you need that $10,000 now. You don't need it distributed over a period of 40 years. And so we can calculate the cost of electricity with the capacity factor of 25% and 8,760 hours per year. This 1 kilowatt system will provide you with about 2,000 kilowatt hours of electricity in that year. And so you divide those two out and you find that this corresponds to about 30 cents per kilowatt hour of electricity. This is twice what we pay for the grid, so maybe we wouldn't do that. But the truth is you can get a 1 kilowatt system for way less than $10,000 now. There are additional costs, such as maybe you need to clean the system, maybe you need to take it down when you're done. How do you calculate these costs in? Well, what you do is you convert them to the present value by using your present value factor, and you just add them to the initial present value with the calculation of your mortgage. What about fuel costs or operation and maintenance costs? You would just add them on every year. And so we can calculate the cost of electricity. It's the cost of producing the electricity divided by the amount of electricity produced. And this would apply for any other energy, like if you wanted a water heater or the purchase of a car. The total costs are the fixed cost, the mortgage, plus the operational cost, the fuel and the operations and maintenance. And the amount produced is a total power times the amount of time that you're producing that power. Wow, my electrical bill from long ago, you can see that the generation cost is actually only about half of the cost. The distribution costs are significant. And we also see that since I've invoked increased efficiency measures in my house, such as LED lights, my electrical bill has gone from $60 to $20 a month. Wow. Okay, let's take a look at Moore's Law, or the learning curve. Moore is well known in the computer engineering business as someone who said, hey, every year and a half, we're going to double the performance of our integrated circuit chips and cut the price in half. And his law has held so profoundly well over the years. Here we see the different years, here we see the processing power, and here we see the number of transistors in a chip. What Moore's Law essentially states is as you build more things, you get better at it. And that's going to apply across a broad range of technologies. But in particular, it should apply very well to solar energy, to photovoltaics, because photovoltaics are essentially a silicon industry. And so here we can see this is the cost in dollars per kilowatt, not per kilowatt hour. So this is the capital cost in 1990 dollars as a function of the total cumulative megawatts installed. So what it means is here in 1963, we had a total of about 1,000 megawatts in gas turbines, and that's a gigawatt. And you can see how the price has decreased over the years as the turbines have improved. We see the same for windmill, we see the same for photovoltaics. And so what this means right now is photovoltaics are more expensive than gas turbines, but they're moving down at an exponential rate. It's also worth noting that the cost of the gas turbines is only part of the cost of electricity. We still have to get the electricity to you. Our learning curve analysis says that the cost of producing at a certain volume, C sub V, is the cost for the amount of volume produced at that time. And this is the cost of the original volume. And that ratio is going to be the ratio of the volumes to some exponent B. And so this cost should be less if the volume is more. So therefore B should be negative. And what we find is that every time you double the capacity, that is the total amount of stuff that you've ever produced, you get a 20% reduction in cost. Accordingly, B should be about negative 1/3. And we can see this very clearly if we look at the wholesale price of photovoltaic as a function of how many photovoltaic cells have been produced total. And we see a very linear graph. Moore's law holds wonderfully. Keep in mind, this is dollars per watt and not dollars per kilowatt hour. This is just the capital cost. An analysis will show you that the slope of this graph is about negative 1/3. What about distributed generation? Why do you get an added value? Well, one, the proximity to your business means that you don't have to pay the grid costs. The waste heat produced, which is considerably more than the amount of electricity produced in most efficiencies, might be of value to you. And you're displacing natural gas. To displace natural gas used to be $8 per million BTUs, but now is less than $3 due to the reduction in natural gas price resulting from widespread fracking. And so you might be able to heat water or your buildings with about 85% efficiency with this waste heat, and the cogeneration will bring you an added value of 2 to 7 cents per kilowatt hour electricity produced. This would essentially reduce the cost of electricity because you're getting that free co-product of heat. So hopefully we understand the exponential nature of finances and how we can represent them with a semi-log graph, how to calculate the cost of electricity production in busbar cost, and how technologies become cheaper as we get more practiced at producing them.